Hey students, got another great question here from chapter 21. It's number 25. Let me give it a try here. It's about charging batteries or using batteries and their internal resistance again. It says, what is the internal resistance if the voltage source, of a voltage source, if the terminal voltage drops by 2 volts when the current supply increases by 5 amps? So, in other words, if I have a battery, and so I'll just kind of make the symbol for the EMF, and then put a internal resistance, and then this represents the battery. Sometimes I like to put a little dotted line around it to represent physically these are one big thing. This is the, chemicals inside right here, and then all the metal connections and all the material connections to bring them together. And so these are the terminals of the battery. All right, and so I hook this up to something. Okay, and so here is the load, if you will. And so this load is going to have some voltage on it. Let's call that V1 for a moment, because coming out of this battery would be current number 1 that goes through this load. Okay, but you'll notice here, the question is, what is the internal resistance? So we're looking for R, the little r, not the load. What is the internal resistance of a voltage source? And so we don't know this value. If the terminal voltage, though, drops by 2, when the current is increased by 5 amps. So in other words, what we're saying here is if you continue to have this same battery, okay, so it's got the same EMF inside, and it's got the same internal resistance, and so here's the terminals of the battery. And then you put on let's say a smaller load. So let's just say less than R. Because that makes the current go up. And so the current coming out of here is now what it was before, I1 plus 5 volts. And that's kind of what they're saying here. When the current supply increases by 5 amps. So we've lowered this load resistor. So the current coming out of the battery goes up. Of course, the EMF doesn't change and the internal resistance doesn't change, but it goes up by 5 amps. Okay, and now what we're going to say here is we get a V minus 2. Whatever that voltage was, it now drops by 2. Okay, and so that's what this question is. Can you find VR? Okay, so if I was kind of doing a loop here, I guess I would do something like this. Maybe I'd start here and applying my math to this first equation. I would say, okay, I have an EMF. Then there is a resistor. And the voltage change is current 1 times resistance 1. And since I'm going with the current, I'd call that a minus. Okay. Then there would be a voltage change. And in this case, I could call it current 1 times R. But let me just go ahead and say, well, what that gives me is some terminal voltage, and I'll just call it V1. I'll put the minus sign because I'm going with the current, but instead of putting it as I1R, I'm just going to put it as a V1. Anyways, that would finish the loop, if you will. Now, if we apply that same thinking to this second scenario where we lowered this resistance, and that's my hint of why I wanted to stay away from the resistance. I don't know how much I lowered it by, but I do know how much the terminal voltage did. So I want to kind of write that in there. But doing the same logic, I'd start here and I'd say, okay, well, there's an EMF here. Then there is a minus the current, and so the current would be I1 plus 5 times R. So again, going with the current, so it's negative, and the new current has gone up by 5 amps, but the same internal resistance. Then I would get here, and I would go minus, and it would be a V1 minus 2 completes the loop. And what's nice here, if we kind of work this out, is we got the EMF. We got minus I1R here. Let's see, this would be a minus 5R. And so I'm just going to do the distributive property on here. And the same thing here, I'll do a distributive property. This will be a minus V1, and this minus and minus make a plus 2 equal 0. But I will notice that these three together equal 0. So this and this and this all equal 0. That's what I get when I combine these two equations together. All right, so take that one, this term here and this term here, call that, and set that equal to 0. So these three is equal to 0. That means I just have a minus 5R plus a 2 equals 0. So moving the 5R to the other side, and then dividing it by 5, I get 2 over 5, which is the same as 4 over 10, which is 0.4. So if I've done my math right here, I have an internal resistance of 0.4, and let me put my units, ohms. So that's the easy part here. Now, the second part, I don't know if there's much I can do. It says, can the EMF of the voltage source be found from this information? And sadly, no. I guess conceptually, I'd say, well, if you just increased that one, of course, we would increase that one, and all the other terms come into play. And see, that E factors off once we combine the two equations together. So everything we did would have no effect on the value of E. We just, we don't know that. We have no way of getting that. Oh, by the way, also in that is the current, I1. So we have no way of having the mathematical ability to solve for the EMF or E1. What we did do, though, is we were able to put this together here to eliminate this and leave us with one equation and one unknown, and so we can solve for that one unknown. So we can solve for the R, but it's impossible for us to get the other parameters in this equation mathematically. So, no. All right. Hope that was helpful. Take care.